Hi guys, all right, today's topic is continuity, so day 7. So what we're going to look at is whether a function is continuous. It says a function is continuous if you can draw without lifting your pencil. So polynomial functions are definitely continuous. That would be like drawing a parabola. It'd be drawing a cubic function, right? We can draw them without lifting our pencil. Discontinuity occurs, two special scenarios. We have what's called removable discontinuity, when a hole exists, right, because there's no value there at x equals 2. And another one is called jump discontinuity, when, if you're drawing this guy, you have to lift your pencil to go from this function to the next one. So these are two types of functions that when you look at them graphically, you can see that they're discontinuous. Now, the jump will stay discontinuous always because you can't make this a function anyway. It would fail the vertical line test. But when you have just a hole like this, we do call it removable discontinuity because we could fill the hole. But we'll talk about that later. All I want you to know right now is just that continuous is when you can draw without lifting your pencil. Discontinuous is when you have to lift your pencil. So there would be a hole here, or you could have a piecewise function. Okay, so what we're going to do is we're going to test for continuity algebraically, so without looking at a graph. So there's 3 steps that you have to complete. So it says a function f of x is said to be continuous at a point C if the following conditions are satisfied. All right, so the first one is a function value exists. So what does that mean? It means at some value C, so maybe like f of 2. So that means if I go to 2, then there's a partner of y. So the function is defined at that value. The limit exists at that same value, which we have been doing, approaching from the left and right. And then if 1 and 2 equal each other, then it is continuous at that point. So that's what we're going to work on today. It says if one or more of those conditions fails to hold, then it is a point of discontinuity. If f of x is continuous at all points on some open interval a to b, then we can say that it's continuous. If it's continuous from negative infinity to infinity, we can say continuous, or we can say continuous everywhere. So just some vocabulary. But this is going to be the most important thing that I'm going to teach you today. Just the 3 steps. So let's just look at the 3 steps. So these 3 steps right here, let's look at those examples of them graphically. So just so you understand what it is when we're doing it algebraically, so we can envision it. So if I want to know if this first one is continuous at C, the answer is no, because this would be the first step. F of C is not defined. Right, there's no value there. So if I asked you what the value was at C, there is none. It's a hole. If I wanted to know the next one, if this one is continuous at C, so this one would be no, because this would be number 2. The limit as x approaches C of this function does not exist. Right? If I approach from the left, I'm going to land here. If I approach from the right, I'm going to land here. Those are different y values, right? Different heights, so the limit does not exist. And then if I want to know if this guy is continuous at C, this graph, the answer is no, because there is a function value, right? There it is. The limit exists, right? It's going to be the same for each one, but those are not the same values. So this would be number 3, where f of C does not equal the limit as x approaches C. Okay, so these are just examples graphically of why a function would not be continuous. Okay, so we're going to use these 3 now, though, but we're going to do it algebraically and not look at the graph. All right, so here we go. So are they continuous at C? Okay, so we're trying to figure out if it's continuous at a point. So we're going to do our 3 steps. Now, I made 2 separate questions here, but space is an issue for me right now. So I think what we'll do is we'll do this first one we'll do this up here, the work, and then I'll use the space for the other guy, because it's two separate questions. So let's do this first one up top. So I want to know if this is continuous at 2. So we're going to do 3 steps of continuity. So here's my first step. Let's see if there's a function value. So is there an f of 2? So if I try to find f of 2, and I plug in right here to my function, 2 squared minus 4 is 0, 2 minus 2 is 0. So f of 2, it's 0 over 0, so there's a hole. So therefore, it fails immediately. There's no function value. So we could stop, but I'm just teaching you this, so I want to just, let's just do the 3 steps anyway. But as soon as it fails, you're done. Like, this is not going to be a continuous function. But let's just do all the steps. Okay, let's pretend that we did get a value there. So limit as x approaches 2 of f of x. So remember what we would do. We would plug in the value, right? And look, we would get a hole. But then remember we would factor. So we have dots on top. This goes back from the other lessons. And now I would replace in, and I would get a value. If I plug in 2 right here, the limit is 4. So I would get an answer for the limit part. And then your third step is to see, do the first 2 steps produce the same answer? So do those equal each other? Well, no, obviously, because the first one we couldn't even get anything, and the other one was 4, so this fails. But as soon as it fails one time, like, you're done. So this is discontinuous. Okay, but I want you to practice all 3 steps for now because you're just learning it. Okay, so let's do the same thing for this other function. So now I'll do this one down here in this space. Okay, so is this function continuous at a point? If I want to know if it's continuous at a point, we're going to do our 3 steps of continuity. So first thing we'll do is see, does a function value exist? So g of 2. So now I have to figure out which domain should I plug it into. Should I plug it into this one or this one? Well, no, it makes sense to plug it into x equals 2, right? So the answer is 3. So the first condition is satisfied. So I do have a function value. Next, I'll take the limit. Okay, and this is the same, obviously I'm using the same thing. So we already did the limit up above, right? We would factor it, we get 0 over 0 whole, and then we plug in and we get 4. So this, I'm able to find something. But now let's take a look. Does the function value equal the limit? Do they equal each other? No, because 3 doesn't equal 4. So therefore this fails, and this would be another example of where it's discontinuous. Okay, so different ways that it can happen. All 3 conditions need to work. So now let's do an example of one where it does work. Okay, all the conditions work. Let's do this guy. Okay, so again, how are you going to know to do these 3 steps? It's when they're asking you to find out if something is continuous at a point. So we'll set up our 3 steps. First one, is there a function value? And we're looking at 0. So does a function value exist? Well, cosine of 0. So what is the cos of 0? So some of you guys like doing that whole, going around with the points, or some of you guys I've gotten you into doing just remembering what the graph looks like, right? So what is the cos of 0? The cos of 0 is 1. Okay, so first condition is satisfied. I have a function value. Next, let's find the limit as x approaches 0. All right, so if we want to find the limit, we're just going to approach from both sides, right? Now this graph keeps going, right? Goes back down this way. So does the limit exist? Well, if I come from the left, I land at 1. If I come from the right, I land at 1. So the limit exists. So the limit is 1. So condition 2 is satisfied. How about condition 3? Does the function value equal the limit? And the answer is yes. So we proved it. They said show that this is continuous. And we did. Why? Because all 3 conditions were satisfied. Okay, so it's 3 steps to continuity. Okay, next one. All right, this is crazy. There's a lot of work going on here on this next one. Okay, so we just did ones where we asked if it was continuous at a point. Now what I could do is I could ask you to use the 3-step continuity test to determine whether or not the function is just continuous in general. Is it continuous throughout the entire thing? I'm not giving you the points. Well, if I give you a piecewise function, you have to use the x values where the pieces meet to see if it's continuous. So we're going to make a little chart here. And where do those pieces meet? Well, the first one says x is greater than 1, and then the next domain says x is greater than -2 and less than or equal to 1. So we can see that x equals 1 is a point where they're meeting. And then the last piece of the domain says x is less than -2, so we can see that x equals -2 is also a piece where they're meeting. So you have to decide what those x values are. And now we're going to go through the same exact steps. Everything we just did, we'll do again. And we'll just do it for this piecewise function. So first thing, let's see if a function value exists. So f of 1. So which piece of the domain do I plug f of 1 into? And I think that would be right here, right? X is greater than or equal to -2 and less than or equal to 1. So we'll plug in 1 into this piece right here. So 5 minus 3 times 1 is 2. So were we able to find a function value? Yes. So the first piece is satisfied. Okay, now let's take the limit. As x approaches 1 of f of x. In order to take the limit, I need to come from both sides for this piecewise function, right? So we're going to take the limit as x approaches 1 from the left, and the limit as x approaches 1 from the right. Okay, so which piece of the domain, I'm just going to erase this now. Okay, so which piece of the domain do I use if x is going to be less than 1? So which piece am I using there? X is less than 1. It looks like I'm right in this piece again, right? The same one? Okay, so we wind up with 2. Now we're going to take the limit as x approaches 1, but it's going to be a little bit bigger than 1. So if it's a little bit bigger than 1, then it looks like I'm plugging it into this piece. So if I plug in 1 right here, I'm going to wind up with 0 over 0, which is a whole. So what do we have to do then? See how this is like a lot of work going on within this question, like all stuff from the other units come in. So I'm just going to put it over here, 0 over 0 whole. So now we have to like fix that up, right? We either have to simplify, top, bottom, rationalize. So I'll just move over to the side. I think we see we have to rationalize the denominator, right? And that's what we did on the previous lessons building up to this. So I'll multiply by the conjugate over itself, right? Because that's just an equivalent expression. I need more room. Okay, so on the top, just like we did previous days, leave that guy alone. Don't FOIL that out. And then on the bottom dots, take the first one and square it, take the second one and square it, and then we'll see these guys wipe out, and I'm left with just this. So now if you go ahead and plug in 1, right, if we plug in 1 now, we're left with 2. So these guys are the same, so therefore the limit exists. So we see how all the work from the previous days is involved in this. Okay, so now we have to do our third step. Oops. Okay, our third step. And the third step is, oh, goodness. Ay, ay, ay. Okay, third step is, does the function value equal the limit? And they do, right? We got 2 for both of them. So all 3 conditions are satisfied. So at x equals 1, this is continuous. Okay, but that's not what I want to know. I want to know if the function is continuous. So now I need to go over to my other column, and I need to see if -2 is also a place where this function is continuous. And if it is, then the whole entire function is continuous. All right, here we go. So let's see if first step, let's see if a function value exists. Okay, let me erase some of this stuff. Okay, so which piece should I plug this one into? -2. So it looks like we're plugging it in right here, right? X is greater than or equal to -2. So if we plug in -2, we get 11. Okay, so the function value exists. Now let's take the limit. So the limit as x approaches -2 of f of x. So we have to approach from both sides. The limit as x approaches -2. Oh, not -2. Whoopsie. Okay. The limit as x approaches 2 from the left, and the limit as x approaches 2 from the right. Okay, so the limit as x approaches 2 from the left. So a little bit less. Oh, the -2 should be right in there. Get that in there. Okay, a little bit smaller than -2. So I think we'd be plugging into this one right here. If we plug in -2, we're left with -1. And now the limit as x approaches -2 from the right, so a little bit bigger than -2, so that would be this domain. And if we plug in, we get 11. So here, these guys are different, right? So therefore, this condition is not satisfied. So as soon as you do get the condition not being satisfied, you can stop right there, and we can say that it's not continuous. If you wanted to do the last step, you can. F of -2 does not equal the limit as x approaches -2. But again, it already failed. It already failed on step 2. So therefore, because it was not continuous at both of the points, this one it was, but not this one, we will say that this function is discontinuous. Oh, sorry. Yikes. Okay. Alrighty. Okay, let's move on to the next piece. All right, so now what I want to do is I want to give you just a rational function. Number 4 is just a rational function. I'm still going to ask you, is the function continuous everywhere? But we're going to look for holes, and we're going to look for vertical asymptotes, right, with rational functions. So let's see. Remember how we do that from that big unit of rational functions? So you're just going to factor. factor. And remember, you would look for the common factor, and that's where the whole would exist. And we would set that equal to 0. So we know that there's a whole at x equals 3. And then remember, we would take the remaining piece of the denominator and set that equal to 0. And that's where my vertical asymptote would exist. So at x equals 2. So I want to know, where is it continuous? Well, I know at both of these points it's going to be discontinuous, right? So I like to just make a quick little number line, put those values on, and now those are the places that it's not continuous, but I want to know, where is it continuous? So we can just use interval notation. So this is where I say in class, where I'm like, I take my fingers and I put them at these 2 places to write the interval notation. So it's negative infinity to 2. Remember, infinity can never be included, so it's a parentheses. This guy's also parentheses because we can't include it. All right, and I have another spot. It's going to be 2 to 3. Right, it'll be continuous along there as well. And the last piece would be 3 to infinity. Okay, so we're just looking, where is it continuous? Okay. All right, let's go back to a piecewise again. And now what I'm asking you to do is I'm asking you to find k so that it is continuous. So what I want to do is I want to make this continuous. So here's how we make it continuous. And it's not that hard. It's just like same steps every time. If I want to make it continuous, find out what the problem is up here, right? And what do I mean by that? Well, it says that you can't use 4. So take 4, right? It says you can't use 4. Take 4 and sub it in and see what y value you get. And we wind up getting 32. So that means that in order for this function to be continuous, 432 has got to be a point. So go down to the piece that has k in it and see, look, this is my x, right? And this is your y. So take your y value and set it equal to 32, what I want that value to come out to be. And we get k to be 31. That would make this continuous if our k value is 31, because look, 31 plus 1 is 32. We would be filling the hole. So I'll say that again. If they want you to make a piecewise function continuous, then figure out like what the problem is. So what is x not allowed to be? Take it, plug it in, and then whatever that number comes out to be, set the one with k equal to that, and then you'll be able to fill the hole. Okay, so that's making it continuous. We'll practice that one again right here on number 6. Okay, so same thing. It says find k if the function is continuous at x equals 1. So we want this to be continuous now at x is 1. Okay, so use the one that doesn't have k. So for this one, they're not giving me a not value, but use the one that doesn't have k. Plug in 1. And we get 8. So that means that we want 1/8 to be a point, right, for both pieces. If it's going to be continuous, it means 1/8 has got to be a point for everybody. So isn't this my y, right? So I want that y value to be equal to 8. Now I know what x is. X is 1. So 1 plus k equals 8. So we get k equals 7. Okay, so that one was a little different. That one didn't have like the not equal, but you can't work with the 2 variable piece. So use the piece that you could sub into first. Okay, so now 7, I wanted you guys to try doing. 7 says state whether the function indicated is continuous at 3. If not, give a reason. So this is the one where you do the 3 steps of continuity. So go ahead and you guys practice both of these. Pause the video, and then you can come back and see how you did. Okay, here we go. So I got both of them to be continuous. It says state whether the indicated function is continuous at 3. So remember, if I want to find if it's continuous at a point, you do your 3 steps. Is there a function value? Does the limit exist? And does the function value and the limit equal each other? Okay, so I did it for both of them, and there we go. All right, guys, we're going to stop here. We don't need to do the rest of that stuff. And I think homework is probably going to be that page 45. I think that's best, and then I'll send you a picture of the answer key. All right, have a great day. Bye. Thanks for working hard.